So here's another problem. This is one-dimensional motion with constant acceleration. This is horizontal, and we're going to take a look at this particular problem. The general expressions that we would want to work with, if we're using constant acceleration, these would be the most common expressions I would use, and I'm going to say these are going to be really helpful for us today. So here's the problem. The scenario is we have a police car who is hiding here behind the bushes, see my pretty bushes, and he notices a car go by him that's clearly speeding. We're told that the car is traveling at a rate of 40 meters per second. It is speeding. Now, the police car is, of course, sitting behind the bushes, so his initial velocity is 0. But the instant that the car passes him, he starts to accelerate. He accelerates with a rate of 4 meters per second squared. We're trying to figure out how long it'll take until the police car will catch up with the speeding car. This problem is actually made a little bit easier because of the fact that we're assuming that the police car starts accelerating the instant that the car passes him. So right when they're at the same location, he starts his acceleration. Now, in order to use these expressions, what we've talked about is you want to make them very particular to your scenario. That is, you put in the correct values for x naught, v naught, and acceleration, so they're describing the object that you're interested in. In this case, we have two different objects. We have a car and we have the police car. So for the car, I'm going to do those expressions first. The car, we are going to say that both the police car and the car have initial positions of 0. We can put the origin wherever we want, and so that's just fine. His initial velocity is 40 meters per second. But he doesn't accelerate, so it turns out that his position can always be described by the expression of just 40 times t. His velocity is kind of boring because he doesn't accelerate. It's just 40 meters per second, which is his initial velocity, but it's also his velocity the whole time. Now for the police car, for his position, again, he is also beginning at x naught equals 0. But his initial velocity was 0 as well. So the only term here is 1/2 his acceleration times his time squared, which turns out to be 2t squared. So that's how we describe the position of the police car. His velocity, his initial velocity was 0, so his acceleration is 4. So his velocity can be given by 4 times t. So the question is then, when does the police catch the car? And we have to ask ourselves, what do we know is going to be true at that time? Now, we might initially think that if they're traveling at the same speed, maybe that's when the police car catches up to the speeding car. But if you think about it, there's nothing that requires that two independent objects that are moving with the same speed are at the same location. And that's what we really want to be true. We want the police car to be right next to the speeding car because then he's caught up. So that answers our question. We want the position of the car and the position of the police to be the same. And now what we can do is we can use these expressions for their two positions and set them equal to each other. The car being 40 times t, the policeman being 2t squared. If we can solve for the time when that satisfies that equation, we have our answer. So this expression that we have to find the time that satisfies that is kind of easy because it doesn't have a constant term. If there was a constant term, like just a number, we'd have to use the quadratic formula. But because both these terms have t and I can factor out a t, and then I can say, well, these two factors multiplied by each other have to give 0, which means one of them has to be 0, and that's how you get the product to be 0. So either t is 0, or the quantity in the parentheses is equal to 0, the 2t minus 40. So if we solve for time in both of those situations, we see that the police car and the car that's speeding are at the same location at t equals 0 and t equals 20 seconds. Now you might initially think, why did t equals 0 come up? And keep in mind that this is just the math of the problem. We are just asking, when are these two positions the same? And it turns out that when we started, they were at the same position. That's how we started. But we used the physics and knowing what we're looking for to say, well, that's not what I was asking. I was thinking for after they both start moving, then when are they at the same location? And the answer to that is the 20 seconds. That type of thing happens a lot in physics, where you're going to get mathematically two answers, and you have to use a little bit more physics know-how or just common sense to be able to pick the correct answer. Here in this one, it's also kind of nice to see why 0 came up as a possibility, and understand that yes, they were at the same location at 0 seconds, but that wasn't when I was interested in. I wanted to know at a later time, when were they at the same location.